Hi, my name is Jonah Botvinick Greenhouse, and this summer I participated in UCLA's Institute for Pure and Applied Mathematics Research and Industrial Projects for Students program. The project I was a part of was sponsored by the Air Force Research Laboratory, and I worked with a team of 3 other undergraduates remotely on our project, An Unstructured Mesh Approach to Nonlinear Noise Reduction. Our academic mentor was Casey Johnson, and our industry mentors were Dr. Robert Martin and Dr. Daniel Eckhart. So here are some quick photos of my teammates this summer, and we were all located on the East Coast, which conveniently made organizing our Zoom meetings a little bit easier. So the Air Force Research Laboratory is very interested in studying Hall effect thrusters, which are ion thrusters placed on satellites in orbit. And as is the case with any type of data acquisition, signals sampled from Hall effect thrusters often accumulate a lot of noise. And so the goal of our project was for any smooth chaotic attractor to denoise a corrupted signal using a clean signal sampled from the same system. So here's a very noisy signal. And by the end of the presentation, I'll explain how, given a clean signal originating from the same system, we can use information encoded in that clean signal to get rid of some of this noise. So we can't start right away with the Hall effect thruster system. We first considered a test case that was more controlled, the Lorentz system. And so on the top left, we have the Lorentz system in 3 dimensions and time series projections onto the X, Y, and Z axes for the Lorentz system. So now the question is, for these time series projections, how can we find information about one in another? And so we can take advantage of Taken's theorem, which essentially says that for a high enough time delay embedding dimension, the embedded shadow manifold will be diffeomorphic to the underlying state dynamics. So you can think about this intuitively as saying, if you have a state variable x of t, and you plot x of t against x of t plus tau, against x of t plus 2 tau, eventually what you get will tell you information about the entire system. And so we do this below for the Lorentz system in 2 dimensions. Here's x of t against y of t, and here we have x of t against x of t plus 2 tau, and we call this our shadow manifold. And you can at least visually see the one-to-one correspondence that might arise between these manifolds. So in the past, a denoising algorithm utilizing a uniform mesh was implemented by the Air Force Research Laboratory. However, the density of our data points for these attractors is highly non-uniform, so the uniform mesh cells do not adapt well to the data density. Whereas if we implement an unstructured mesh, where the cell size does adapt to data density, we're going to achieve more desirable reconstruction results. So for our project, we considered an unstructured mesh, shown on the right here. And so the type of unstructured mesh that we utilized is known as a Verneuil diagram, and it's based off of a nearest neighbors approach. So we first randomly sample a subset of the data points, and for the rest of the points, we just determine which point in that subset does it have the closest Euclidean distance to, and we form the groupings accordingly. And so now you can think about this reconstruction method as an algorithm where the input is a clean signal x of t and a noisy signal y of t, and the goal of the algorithm is to denoise y of t. So the first thing we do is split our data into training and testing phases, time delay embed the training and testing phases from the clean signal x of t to form the training and testing manifolds, and then we overlay a Verneuil diagram, the same Verneuil diagram, on both the training and testing manifolds, shown in green and blue at the bottom here. We can then associate every data point on the noisy signal to a point on the clean training manifold with one-to-one correspondence. So we group together all the points on the noisy signal that map into the same cell of the clean training manifold and compute their average value. We then repeat this process for all cells of the Verneuil diagram. Using these average values, we then form the reconstructed signal. So for all the points on the testing manifold that reside in the same cell of the Verneuil diagram, at the times that these data points were sampled at, we assign in the reconstructed signal the average value of that Verneuil cell. So here, using this algorithm that I just described, we begin with the noisy signal that I showed you at the beginning of the presentation in the bottom left. Using this algorithm, we form the reconstruction shown in the top right, which very closely mirrors the dynamics of the true signal shown in the bottom right. And so that was for the Lorentz system. And for the Lorentz system, we also showed that the algorithm exhibited statistical convergence. What this means is that the error decreases linearly on a log-log plot as we add training data. And so you can think about this intuitively as saying, we can make our reconstruction match the original signal as closely as we want, provided that we have a sufficient amount of training data, which for the Lorentz system, we always will. We were then able to apply our algorithm to the Hall effect thruster system. So shown on the left is a 2-dimensional projection of the training manifold of the Hall effect thruster system. So oftentimes the Hall effect thruster system is very high dimensional, so we had to conduct our time delay embeddings in usually more than 8 dimensions to get desirable reconstruction results. So this is just a projection of the manifold, but it gives you some idea of what the data might look like. So on the right, we have our reconstruction, and we can see it very closely matches the true signal we were given from the Hall effect thruster system, which was very exciting to see our algorithm working on a less controlled system than the Lorentz system. And so just to conclude, we developed a new denoising algorithm based on an unstructured mesh approach. We showed that in the case of the Lorentz system, the algorithm exhibits statistical convergence. And for the Hall effect thruster system, we also produce promising reconstructions. And so with that, I'm happy to take any questions.